Okay, we're continuing with the lecture on magnetism, particularly applied to electromagnets and so forth, right? So this is a simplified version of an electric motor. In an electric motor, we basically have something that looks like a horseshoe magnet. It's oriented like this, where you have the North Pole here and the South Pole here, and the magnets are one unit here. Inside this, you have the yellow coil of wire. You have a battery. In this case, you send a current through this wire, which goes to this connection to the yellow wire, travels through this wire, comes back to the battery. Now, in the earlier lecture, we had said that in the presence of a magnetic field, say from the North Pole to the South Pole, if we send a current through a wire, the wire would deflect upwards or downwards, right? Because of the interaction between the magnetic field lines and the current carrying elements, in this case electrons, right? Or the entities or the particles that are carrying the current. So when the electrons move, say in this direction, that means a current is moving in this direction. So you've got a current traveling in this direction, you've got magnetic field lines in this direction. So current in one direction, field lines in this direction, and that creates a force that goes along my thumb, in this case, in a direction that's perpendicular to the other two. So since the current is traveling in this direction, the field lines are in this direction, what will happen is there will be a torque that will there'll be a force on this coil that will cause it to rotate. It will cause it to rotate, and it will try to line up. In this case, you can see that the torque is causing it to rotate in this direction, and we'll try to get that coil to line up like this. So what you do, as soon as it lines up like this, as it gets close to this, you flip the direction of the current flowing in the coil. So if the coil was like this, you send the current one way and it flips like this. You now switch the direction of flow of current in the coil, and so the coil decides that this side should be down. So the momentum keeps it going, so it flips again, so this side is down. Then you flip the direction of the current in the coil again. So what was down here needs to be up, so it flips again. You keep doing this and it flips again and again and again, and what happens is you've just turned this coil into a rotating, basically an electric motor. So if this coil is then attached to an axle or something of that sort, that axle will rotate. So that's how your fan operates. Right, so you got an axle that's connected to this coil, and you extend the axle out and you put fan blades on it, switch this on, and now you've got a fan. So that's a simplified version of how an electric motor works, applying the principles that we have seen in the last lecture.
What switches
the direction of the current? In this case, in this particular case, because we're sending a direct current through it from a battery, what happens is, do you see this connection? Do you see that it's a cylinder that's been cut in half? So what happens is, now this half, the upper half of the cylinder is in contact with this wire. So as the coil rotates, this wire, let's say the coil is rotating in this direction. So the wire is in contact as the yellow wire here comes all the way down here, and this wire is going around the bottom half up here. So this wire comes all the way here, momentum keeps the coil turning, the wire then moves into the gap and now contacts the other half. So for half of the cycle, this wire is in contact with the upper half. So let's say that this is the positive terminal of the battery. What happens is this upper half, contact, connector, whatever it's called, is positive and this is negative. So as long as this is in contact with this side, it's positive, so the current is flowing in this direction. When this wire turns around and hits this, all of a sudden this is negative because it's connected to the other end of the battery. So now the current is flowing in the opposite direction through the coil. So that's how you switch. Pretty ingenious, right? Whoever came up with it in the first place. Extra credit to you for asking the question. Okay, next slide. Continuing on with the magnetic field. You're probably aware that the Earth has a magnetic field, right? And here's kind of what it looks like. If you look at the the axis of rotation of the Earth, there's the axis, and the North Pole, South Pole, the magnetic North Pole is shifted a little bit with respect to the North geographic pole, but really it's not the okay. I've actually given you the answer to one of the lab questions. Okay, for now, let's say that this is the north geographic pole, right? In terms of geography, this is the North Pole. What happens is the magnetically north pointing pole, the pole to which the North Pole of a compass points, is sitting here. That pole, that whole axis, so let's call this the North Pole magnetically and this the South Pole magnetically. What will happen is this axis is tilted with respect to that axis. Now, it is believed that what causes the magnetic field of the Earth is, if you look at the Earth like this, you're probably aware that there are different hemispheres in the Earth where there are different densities and different materials and different temperatures as you go from the center of the Earth upwards towards the outside. And somewhere in here you end up with molten lava and so on. So it's believed that there are eddy currents in the molten portion of the Earth, right? A lot of iron in there and so on. So this is the current hypothesis. And as a result of the circulating flow of electrons primarily in these, and maybe positive charge atoms, you end up with, because remember that we said that anytime there's a moving current, it creates magnetic field lines. So these currents then create the field lines that overall get together to create the magnetic field of the Earth, right? Now, if it were not for the magnetic field of the Earth, we'd probably be dead. And here's the reason why. The magnetic field, so you've probably all seen pictures of the aurora borealis, right? Which is near the, generally close to the North Pole. And what is the equivalent in the South Pole? Do the northern lights show up in the South Pole? Okay, do the southern lights show up at the South Pole? You have not? Okay. Anyone wish to guess? Yes. Yep, the answer is yes. Extra credit to those of you who've spoken up. And those are called the aurora australis, as opposed to the aurora borealis, right? But it's similar phenomenon. And what they are typically is like sheets of lighting. It's almost like fluorescent lights, sheets of them in different colors. Like here is pink, or purple, pink, purple. You can get yellow, you can get green, and so on. And that's basically what's happening is cosmic rays, charged particles from space, from the universe in general, from other stars and so on, they come through from the sun too, come through the atmosphere. And as they come close to the Earth, what happens is the magnetic field, these act like a force field. They shield the Earth from these charged particle rays. So the charged particles get funneled away from the bulk of the Earth down here, and they travel down these field lines, and they come in at the South Pole and the North Pole, right? So as they come in at the South Pole and the North Pole, they concentrate in these sheets because of the field lines, and these sheets then become intense enough to actually ionize the molecules / atoms in the Earth's atmosphere, right? So you basically kick an electron out of an atom in the atmosphere, that another electron or the same electron pops back down and gives off light. The same phenomenon that we see here in the fluorescent bulb, or if you happen to be at a bar and you see a neon light in pink or whatever color, right? It's basically a plasma. You're exciting atoms to higher levels, they jump down, the electron jumps down and gives off that excess energy in bright pink, fluorescent green or whatever, same phenomenon. So if it were not for these, we would all be exposed to substantial amounts of cosmic rays, right? And through the history of the Earth, it would have had substantially greater amounts of cosmic radiation coming to impact life on Earth, which would create a lot of, problems with mutation rates that are so high that you would end up ultimately wiping out life on Earth. Okay, the magnetic field. So this is just making the point that the spacecraft Surveyor was sent out into space, I think, and it measured the magnetic field of Mars, ballpark of 1997-ish. The magnetic field of Mars is about 1/800th that of Earth in terms of strength. So Mars is not, from this viewpoint, is not that conducive a place for life to exist. Since we're on the topic of magnetism, it's believed that homing pigeons can sense, they may be able to sense direction because of a built-in magnetic compass within their skull. So it's believed that there's like magnetic particles in their skull that kind of help them to kind of determine which direction is north and so on. I wouldn't be surprised if they have. right? Like the easy way to test this is to put the bird. How do you do this? One possibility, but it's not going to be trying to home. Like put it in one corner of a room and expose it to a strong magnetic field and see what it does, right? Things north is there or here or whatever, right? Another possibility is, if you're trying to get it to home, then is to release it with a little, you can like tape a thingy, like a collar on some of these. Put a collar or something, right, or a wristband around the with a strong magnet that would throw off the magnet, right? So it says it's like the drunkard's walk, right? Home is there, right? So I need to head in this direction, right? So maybe we'll have the pigeon or the dove doing the same thing. So I wouldn't be surprised if it has been tested. Extra credit if you can come up with an article or something that indicates that to be the case, right? So notice these are speculative words. Anytime you read in science, in a journal or in a textbook, it says words like the pigeon may. That's a weasel word. It's a word that says really we don't know what's going on, but we think it might be. So it's a speculation. It's a conjecture. It's not anything that's proven in any significant fashion, at least at the time of the writing of this book. Or it could be just that the authors didn't know of a scientific article, right, that had shown this to be the case one way or the other. Okay, so reminder for you guys to go over the multiple choice questions, right? And